composition of compounds. The chemical formula, along with the molar masses of the elements in that formula, gives us the relative quantities of each element in that compound. And that's very useful. And that can be used in different ways. One way we can use that is to talk about the mass percent composition or the mass percent of an element. That's the element's percentage of the compound's total mass. So this is something I'd like you to remember because it's very useful, like on an exam where you suddenly blank and you can't remember what percent something means. What is percent error? I don't remember. In general, percent means the part that we're interested in divided by the whole thing times 100. The part and the whole generally have the same unit, and so the units cancel out, and percent here is just the unit. Never ever use the percent button on your calculator. Okay? Don't. That's for something else. It's not for chemistry. Don't do it. So we can determine the mass percent of each element in a compound in two ways. We can use the formula of the compound. So that's one way to do it. Percent of X, X just standing in for whatever we're interested in, would be the mass of X in 1 mole of that compound divided by the mass of 1 mole of that compound. The mass of 1 mole of the compound is the molar mass, right? So that's not too hard to calculate. Sometimes we do it by experimental mass analysis, where you take a compound, you're not sure what it is, you break it into its elements, you measure the masses of the elements, and then you calculate the percent composition that way. So there you identify the mass of the element that you're interested in, you divide it by the mass of the compound, you multiply by 100. So if you take the percent by mass of each element in a compound, they should add up to 100%. In practice, they'll get close, but due to errors in measurement or rounding, it might be a little bit off. You could end up with 99.9% or 100.5% or something, just from rounding. Okay, acetic acid is the active ingredient in vinegar. That's what gives it its acidic properties and its distinctive smell. Calculate the mass percent composition of oxygen in acetic acid. So we're asked to calculate mass percent. They didn't give us any numbers at all. We don't need any numbers. We can calculate a mass percent from this formula, the chemical formula. So this is a problem where we're going to use an equation. So we're looking for percent oxygen. So the percent oxygen is going to equal grams of O divided by grams of C2H4O2 times 100%. The units gram cancel out. The usual way to do this, which is the easiest way, is just to say, well, let's look at 1 mole of this compound. What's the mass in grams of 1 mole of C2H4O2? Well, we can calculate that, right? So for C2, H4O2. The mass is 2 times the mass of carbon plus 4 times the mass of hydrogen plus 2 times the mass of oxygen. Two times carbon, 12.01, plus 4 times hydrogen, plus 2 times oxygen. Push the wrong button. You get 60.052. Anybody else get that? Yeah, thanks. You know, anytime you do a calculation like this, especially if it's on an exam, it's worth just taking a couple of seconds and typing it into your calculator again. Make sure you get the same answer. If you get a different answer, go for best 2 out of 3. So easy to push a button wrong. That's the mass of 1 mole. of the whole compound. So that's going in the denominator here. What's the mass of oxygen in that 1 mole of acetic acid? 32. It's this right here. That's the mass of oxygen. Because each of these units has 2 moles of oxygen in it. So if you write this out, write this calculation out, all you have to do is pick out the element that you're looking for, and that's what goes in the numerator. So you can put 2 times 16 up there, or you could, finish the math. It's 32 grams of oxygen times 100%. So I've got 32 divided by 60.052 times 100%, and how many significant figures should that percentage have? 4. Because I used molar masses that had 4 digits, 4 sig figs, that's going to limit it. If you used all the digits, like this periodic table has more digits on it than what I have in my head, then you could put more. So the number of sig figs you put here is going to depend on what kind of numbers you wrote down. So the way I did it is going to have 4, and so it's 53.29% oxygen by mass. Any questions? Mass percent is useful as a conversion factor. It relates the mass of an element in a compound to the mass of the compound itself. So remember that percent literally means per 100. How many parts per 100 parts? Per million means parts per million. Per billion is parts per billion. So Freon 112 has this formula. It is 69.58% chlorine by mass. So if they give us the percent by mass, we can use that as a conversion factor. We don't actually have to calculate a mass percent. But you would write that down as this means 69.58 grams per 100 grams. It's the part over the whole. You could do it in kilograms or milligrams or pounds or troy ounces. Any unit of mass or weight would be fine as long as you use the same unit on the top and the bottom. So let's do an example with this. What mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. Well, let's write down the numbers. We've got 58.7 grams of iron, that's Fe, and we've got 69.94% iron. And what are they asking us for? Grams of iron 3 oxide. We could write the formula, but we can actually do it without knowing the formula. What would the formula be? What's iron 3 mean? Fe3 plus, and oxide is O2 minus. Nomenclature review here. So Fe2O3 is the formula. We don't need it, but it's good practice. The Roman numeral 3 tells us the charge on the ion, not how many there are. It's not Fe3O something. So we want grams of iron oxide. This percentage here, percent can always be written as per 100. 69.94 grams per 100 grams. It's grams of iron, the part, per 100 grams of the whole thing. Everybody okay with that? So which of these numbers is our starting point for this calculation? It's the grams of iron. This is just a single unit. It couldn't possibly be a conversion factor. This percent is a little disguised that way, but when we remember what percent means, that can be used as a conversion factor. It's the relationship between the mass of iron and the mass of the whole compound. So this is actually one step. So one really long arrow. So 58.7 grams of iron times 1 factor equals. So we're going to have grams of the compound on top and grams of the iron on the bottom. This is where it does become important to specify grams of what. So the grams of iron are going to cancel out, giving us the mass of the compound. This percentage is where we get the numbers. So 69.94 grams of iron is in the denominator, so that's where that number goes. And then the 100 is on the top. When we're looking at sig figs with a percentage like this, and we say it's this many grams per 100 grams, what we mean is it's per exactly 100 grams. This number, 69.94, has 4 significant figures, but the 100 is exact. So 58.7, turn the calculator on first, times 100 divided by 69.94 equals. So this should have 4 sig figs. 83.92, there's 4 sig figs. Toss on a couple extras just in case we rounded wrong or figured our sig figs wrong. So 83.93 grams of Fe2O3. And then look at that and say, does that make sense? If the compound has this many grams of iron in it, should the compound weigh more or less than the mass of the iron? It should weigh more. If you have a classroom that has 15 boys in it, what's the total number of children? Is it more than 15 or less than 15? It's got to be more. At the very least, it's equal, right? Girls do not make negative boys. Yes? Why do I take 4? Oh, that's an excellent question. I'd like to say I was trying to trick you. I wasn't. I was being dumb. I was focused on this. This only has 3, right? So, yeah, mark that on your calendar. I made another mistake. So, not that. Let's see if I can erase this. 3 sig figs, so it's 83.9%. No. Is lecture over yet? Not quite. Dang. And it's only Monday. Haven't recovered from the weekend yet. Okay, is that right? Any other questions? Did I screw up anything else? It's not the only way you can solve this problem. Some of you are really good with percentages. I learned some other ways to do percentages, and you can do that. But this is the most straightforward way for people who do not get percentages. And you can do this with all kinds of things. So that's using a mass percent as a conversion factor. We can also get conversion factors from the chemical formulas themselves. In the formula, though, instead of mass of this to mass of that, we have the relationship between moles of atoms or moles of molecules. So this formula for that Freon 112, C2Cl4F2. If we're looking at the amount of chlorine, carbon, we could say there's 2 moles of carbon per 1 mole of compound. And that's coming from the formula. In the formula, it's C2. There's 2 carbons in 1 molecule, so there's 2 moles of carbon in 1 molecule. For chlorine, it'd be Cl4, so there's 4 moles of chlorine per 1 mole of compound. What would it be for fluorine? 2 moles of fluorine to 1 mole of compound. But just remember, this gives us amounts in moles. It doesn't give us masses in grams. Determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. So we've got 7.2 grams of aluminum sulfate. Following our basic problem-solving strategy here. And what do we want to know? Mass of oxygen. Grams of oxygen. I'm not looking for mass of O2 or anything, because here the oxygen is in the compound, and so the diatomic business is not relevant. Grams of aluminum sulfate, grams of oxygen. How can I get from one to the other? We need moles. We need a mole ratio from the formula, which we weren't given. Got to figure out the formula. What kind of a compound? Molecular, ionic, or acid? Ionic, because aluminum is a metal. So for ionic compounds, we need to write the formulas for each of the ions with their charges first. Aluminum has the symbol Al. What is the charge on an aluminum ion? 3+, because it's in group 3. Can't write the number 3. 3+. Sulfate. What's the formula for sulfate? SO4, and the charge is 2-. Now memorize those. So index cards, you can get them real cheap at the dollar store. And you write the formulas on one side, and you write the names on the other side, and you carry them with you, and you get stuck at the train on Blackstone, and you flip through your cards, right? You're stuck looking for a parking place, you find a spot to just idle, and you look at your flashcards. You're waiting for class to start, and you look at your flashcards. Little bits of time, okay? So how do we put these together? Al2 and SO4 is going to have a 3 on the outside. So that's the formula. So from this, we can get the moles of oxygen to moles of the compound. So that's in the middle here somewhere. Could we go from grams of aluminum sulfate to moles of aluminum sulfate? Sure. Al2, SO4, 3. And for moles of aluminum sulfate, we can go to moles of oxygen. Looking at this and getting the ratio. And then from moles of oxygen to grams of oxygen, that's the molar mass of oxygen from the periodic table. Any questions? So let's write this out. 7.2 grams of Al2, SO4, 3. I know it gets tedious writing that whole formula out multiple times. Deal with it. 3 arrows, 3 factors. After you graduate and start working in your field of choice, you can do shortcuts. The next unit is moles of aluminum sulfate. Moles of Al2, SO4, 3. I know it's tedious. And then in moles of oxygen, and then grams of oxygen. Same pattern. I get bored going forward, so sometimes I like to go backwards with the bottom units. And I frequently don't leave enough space for those long guys. And here we've got grams. It's tempting to just call this Steve or something, but Al2SO43. So grams to moles of oxygen, how many grams does 1 mole of oxygen weigh? 16.00. What's the ratio of moles of oxygen to moles of aluminum sulfate? 12 oxygens to 1. We get that from this formula. This has got 2 aluminums and 3 times 1, 3 sulfurs, and 3 times 4, 12 oxygens. So it's 12 moles of oxygen to 1 mole of aluminum sulfate. And then we need the actual molar mass for aluminum sulfate, so we have to calculate that. So 2 aluminums times the mass of aluminum, 26.98. And we've got 3 sulfurs, 32.07. And we've got 12 oxygens. So this is going to be a big number. That's okay, it's a big molecule. 2 times 26.98 plus 3 times 32.07 plus 12 times 16. 342.17. Grams per mole for aluminum sulfate. Somebody confirm that I did my math okay? Anybody? Yeah, thank you. Okay, so that's the number we're going to put in down here. 342.17. If I wanted to get a calculation like this correct, I would not try to do it in my head by just punching things into my calculator. I would write it out. You should write it out too. You shouldn't try to do stuff like this in your head. So 7.2 divided by 342.17 times 12 times 16 equals. How many sig figs? Just 2. This one at the beginning, the 7.2 grams, is what limits the number of sig figs. So 4.0, there's our 2 sig figs, 2 extras, 4 grams of oxygen. 4.0 grams of oxygen. Is that a reasonable number? Yeah, it's smaller than the overall mass, so it's certainly possible. If I came up with 400, that's not possible. You can't have a family of 5 with 17 children. It's not possible, right? Any questions?